We're looking at motion in gravitational fields, and isn't this an amazing photo? This is the view of Earth from Moon. It's available on the NASA website, and it just shows how delicate and amazing Earth really is with its thin atmosphere, and you can see the swirls of the clouds with the weather systems and so on. And here's the question. What would be the duration of the year if the distance between Earth and Sun is doubled? So we need to ask questions about the question. Firstly, what module is it? It's Module 5, Advanced Mechanics. And we need to say, what type of question is it? In this case, it's a calculation question, but it is a question that requires you to manipulate formulae from the formula sheet. And what's the first step? Of course, the first step is always data.
Welcome to Mr. Max Physics channel. He can explain things really well and is a lot of fun to watch.
Firstly, we need to know that T1 is 1 here. Okay, that's the first bit of data. Now, we can say also, I'm going to do this downwards, usually I go across, but R1 is, let's call it 1AU, 1 astronomical unit. We don't usually use that for things. If we didn't have 1AU, we'd say 365 days. Okay, what do we do now? We've got a movement, okay? The question is that the distance between the Earth and the Sun is doubled. So we've got to imagine this is situation 1. Now we're looking at situation 2 where we look at a new radius. So R2 is twice R1. And we want to find T2. So that's essentially the data. R cubed over T squared. And on the formula sheet, it says it equals something. We're not interested in the something. We're not actually calculating these from scratch. So I'm just going to put K. It's a constant for the solar system. And notice it doesn't have subscripts. So on the formula sheet, it's to calculate it directly given these constants. But we don't, for this question, we don't have those constants. I'm just going to put K as a constant. So once doing that, I can now go, well, what does that mean? It means that R cubed, the first one, over T squared, again, the first one, must equal R cubed 2 over 2. Okay, so we've now got, so it's R cubed on T squared. And now we've got subscript 1, top and bottom. R cubed on T squared, subscript 2, top and bottom. And that's what it means. For the system, it is actually constant. Okay, this is a really good bit. So now we substitute in the data that we have. Okay, so the data that we have is here. Substitute these. Okay, so for T1, which is down the bottom, it's just 1, and we're squaring it. For R1, it's 1, and we're cubing it. For R2 is twice R1. So we'll put brackets to keep things safe, and we'll replace it with 2R1, and we're cubing that. And the bottom line of what we want to find is the period of the second one, so it's squared. Now that's really nice that it's 1 on that side. I'm going to bring the T2 squared up to here, so that's just 1. When you bring that, multiply both sides by that, we've just got T2 squared on the left-hand side. You see that down? Yes. And on here, I'm going to cube everything in the brackets. So that equals 2 cubed is 8. R1 cubed is R1 cubed, and it looks, I'll need to substitute that in as well. So the R1 cubed, I'm just going to rewrite it here, is 1 cubed, which of course is 1. And so now we've got T squared equals 8. So T2 squared is 8. So T must be the positive square root of 8. Can't be negative. Negative has no meaning in this context. And that really is the answer, except we want to probably calculate it. So if we calculated that, we would get something like 2.828 down here. 2.828. Keeps going, round to 2.8. And the units, of course, is years. Y for years. Okay. Not sure if you can see that. For some reason, it's gone there. Yes, just see it. Okay. So we've got t squared is square root of 8, which is 2.8 years. So if you double the distance, we're moving away from the sun, where it's going to take us longer to get round, and that's Kepler's third law. So we've answered the question using Kepler's third law, the law of periods, and we've seen how that can apply to the solar system. Kepler's third law applies to any system. And I'll leave you with this view of Earth from Moon. You can subscribe to Mr. Mac's Physics channel. As always, thanks for listening, thanks for watching. I'm Mr. Mac.